All right, let's go ahead and do some practice problems going over this whole idea of thermochemical equations. And the thing we want to remember is that when a chemical reaction occurs, it's either going to absorb energy or release energy. And we have these diagrams below, which are energy diagrams, and they show us whether or not a chemical reaction is releasing or absorbing energy and how much energy it's releasing or absorbing. And the key thing to keep in mind here is that when we talk about the energy that's within substances, it's hard for us to measure the energy within a substance. For example, it's hard for us to measure the actual energy within the C2H4 and the O2. However, what we can measure is we can measure the change in energy. And so if you take a look at this first thermochemical equation here, notice how it's like a normal chemical reaction. It's not balanced though, and now it is. And notice how it has energy listed as a product. What that means is that the energy of this plus the energy of this is going to be equal to the energy of the reactants there. And so what that's really telling us is that the reactants contain more energy than the products. And so because the products are in a lower energy state, that means that energy must be given off in the form of heat or light. Now in this situation, notice how it's the energy's in the reactants. And so what that means is that the energy plus the energy of within this reactant here will come together to to make the product. And so what this means is that the products in this situation are higher energy. It requires energy for this to become this. And so this first situation happens to be represented by this first energy diagram. Notice how the reactants are higher energy than the products. And so this drop in energy right here is what results in energy being given off. And so because it's lowering its energy is being released to the surroundings. Now there's a couple other things I'm going to talk about when it comes to this diagram. Notice how we've got this first part at the top here. What this is called the activation energy. And if we were to think about gasoline, when gasoline burns, it does give off energy, but it takes a spark to make it start burning. And so a piece of wood, same thing. A piece of wood will burn, it'll give off energy, but it takes adding a flame to it, adding some amount of energy to it for it to start burning. And so that is called the activation energy. It's the energy required for this reaction to occur. And so we're going to talk about this in a moment, but really this has to do with the breaking of bonds. It's how much energy is required to break the bonds. And then this part here, the downhill part is when the bonds come together, they give off a certain amount of energy. All right, so this second thermochemical reaction or equation, notice how the energy is in the reactant side. So that means that this requires energy. That means when we go from reactants to products, when this goes to the product side, it's going to absorb that energy and the product will be a higher energy state than the reactants. And this is this second energy diagram. Now, anytime energy is released, it's an exothermic process. For an exothermic process to occur, you need to go when you go from reactants to products, the products are lower energy. Whenever energy is absorbed, like in this situation here, that's an endothermic process where it's absorbing energy. Now, when we're taking a look at these energy diagrams, it says calculate the change in enthalpy of this reaction, which is the change in energy. And this is very easy. First off, it's going to be a positive delta H because notice how it's starting here and ending here, so it's gaining energy. And it's very simple. Wherever it starts and wherever it stops, the difference of that is going to be the change in energy. So notice how it starts at 250 and it ends at 300. That is going to be a positive 50 kilojoules of energy. Now, this happens to be an endothermic reaction. It's an endothermic reaction because it's a positive delta H, and because we can see that the products are, when the reactants turn into products, they're absorbing energy. Now, this is the same thing wherever it starts and wherever it stops. It's the difference of that. And so notice how, because it's dropping down, it's going to be a negative delta H because it's losing energy. And it's going from 450 to 350, so it's a negative 100 kilojoules of energy. This happens to be an exothermic process because it's losing energy when it goes from reactants to products, and it's giving off that energy. So in this situation, energy is absorbed. In this situation, energy is released. Now, what I want to do is I really want to talk about, what is the activation energy in this graph, and what is the, what results in it being endothermic or exothermic. And so what I'm about to do here, and I know that I'm jumping around the book a little bit, but what I'm about to do here is I'm going to do a problem that you will not be expected to do on the exam. But I'm going to do this problem because it's going to really show us what the activation energy is, which this is the activation energy right here for this particular one. This is the activation energy for this one. And just to go back to the other graphs here, it's these blue parts that are the activation energy. So it's pretty much wherever the reactant starts all the way to the top of the little hump there. Again, reactants, top of the hump, that is the activation energy. That's the energy required to get the reaction started. And so what I want to do is I want to talk about why is there a activation energy, and how do we, what is going on with that activation energy there. So what we're going to do is we're going to look at this bond energy chart. Okay, so we did talk about bond energy, and I'm going to go ahead and draw the Lewis structure of this. So we have this right here plus this yields two of these. All right, so I'm going to draw two of them. And what we want to think about is what is happening to the bonds here and what's happening to the bonds over here. Well, whenever a chemical reaction occurs, the bonds in the reactants break. So these bonds will break. And whenever bonds break, that is an endothermic process. It requires energy to break these bonds. That happens to be the activation energy. The activation energy is the energy it takes to break the bonds. Well, what's happening to the bonds in the reactant side? Well, what's happening is these bonds are forming. The product side. In the product side, the bonds are forming. And so whenever bonds form, that's an exothermic process. Energy is released in the formation of bonds. And so how do we tell if this is an endothermic process or an exothermic process? Well, what we can do is we can actually take a look at these bond energies up at the top here. We've got the H, this one right here, and then we have the Cl-Cl bond here. And then we have the HCl bond, which is right here. Now notice though, and I'm going to change the color. Notice how we don't have one HCl bond forming, we actually have two of them. And so we would actually end up multiplying this by 2. Now, what do these bond energies mean? Again, you will not be asked to do this on the exam. I'm only showing you this to kind of show you how this whole concept works. Well, what this means is these bond energies here, this is the energy it takes to break a bond. It's also the energy that's released when a bond is formed. And so when we take a look at this situation where the HH bond is 432, because we know that this bond is breaking, that means that it is absorbing 432 kilojoules of energy per mole. And we know the units by looking there. And so when this bond breaks, it's absorbing this. When this bond breaks, it's also absorbing that amount of energy as well to break the bond. And so if we were to think about our energy diagram, and here's the reactants, the breaking of the bonds is this first part here. The breaking of the bonds is, and I'm going to make it red, the breaking of the bonds is this part right here. The activation energy is the breaking of the bonds. Now, what about these bonds here? All right, what about these bonds here? Well, these bonds are forming. And so because they're forming, this energy here is not being absorbed, this is being released. And so we have, this is the activation energy, this is the energy being absorbed, this is the energy being released. And so let's go ahead and actually, before I draw the second part of the graph, let's go ahead and actually get these totals here. And so what I've done is I've added these two numbers together because both of these bonds are breaking when the reaction's occurring. And the total amount of energy being absorbed to break those bonds is 671. This part right here is 671. And so let's go ahead and 671. Keep that in mind there. Now when these bonds form, notice how the total amount is going to be 854 because there's two of these bonds forming, and each bond will release 427 kilojoules of energy per mole. So notice how this amount is 8. It's 854. So what that means is that this second part here is the formation of the bonds. And so notice how because the formation of the bonds is a greater amount of energy, notice how the second part drops more. And so this is going to end up being an exothermic reaction. The reason why it's an exothermic reaction is because the energy released when the bonds are formed is greater than the energy absorbed when the bonds are broken. And so this will end up being an exothermic reaction. And then we can actually figure out what the difference between this and this is, because we know that it's going to go up 671, but then it's going to go down 854. And so if we just subtract those, we can get the amount that it changes. And so what you end up with, because you do bonds broken minus bonds formed, you end up with a negative 183. So this here, from here to here, is going to be negative 183. As we go from reactants to products, it's going to be negative 183. So this is what I want you to know from everything I just did right here. I want you to recognize that. Notice how the red part right here is the bond breaking. That's the part that I want you to recognize, is that the activation energy for the most part comes from the bonds breaking. And then this drop right here, this comes from the bonds forming. Now because more energy is released when the bonds form, this is going to end up giving off more energy than it absorbs, so it's going to be exothermic. Now what I'm going to do is, again, I want to really emphasize, you will not need to do any calculations with this. You only need to understand this part of the graph. All right, so what is this graph representing? And so how can we look at this graph and just determine the difference or the delta H, which is kind of like what we did here. All right, now notice how in this particular graph here, this is the bonds breaking here, right? This is the bonds breaking. And I know I got my colors backwards, I'm sorry. This is the bonds forming. So notice how in this situation it doesn't drop as much because when the bonds form, it's giving off less energy than when the bonds break, the amount of energy it absorbs. So let's go ahead and actually start calculating. And again, I know I'm jumping around here. I apologize. So these practice problems are on a different page. But let's go ahead and start actually doing some stoichiometry type problems here. And so first off, I'm going to go ahead and answer number 2. Number 2 is asking, is this endothermic or exothermic? Well, because this is in the reactant side, this is going to end up being endothermic. It requires energy to occur. And so it's going to absorb energy, is going to be endothermic. And it's asking, what is the energy change if 2.25 moles of NaHCO3 decomposes? What's the energy change? Well, 2 moles of this will react with 85 kilojoules of this to produce 1 mole of that, 1 mole of that, and 1 mole of that. And so what we want to think about here is we are given moles of NaHCO3. And before, if we know moles of one substance, we can actually convert it to moles of another substance. For example, moles of CO2. So this is what we were able to, this is what we've been doing almost this whole semester. So if you know moles of one substance, you can convert it to moles of another substance. Well, the only thing I'm going to add is, notice how in this situation we're going from here to here, right? Well, we can also go from here to the water. We can go from here to the sodium carbonate, and we can also go from here to the kilojoules. And so that's the connection I want you to make. We can go from moles of one substance to kilojoules required for this to occur. And so we're going to go from moles of one substance to kilojoules. And so this is the new part that we're going to do. So again, once we know moles of any substance, we can convert it to kilojoules, either absorbed or released based off of how many what quantity we have of that substance. And so in this situation, we have 2.25 moles of NaHCO3, okay? And we can go moles of NaHCO3 to kilojoules. So we can go from moles to kilojoules. And we know that 2 moles of this will react and consume 85 kilojoules of this. And so this ends up being 95.625, but with sig figs, it ends up being 95.62 kilojoules of energy. Now, is this a positive 95.6 kilojoules, or is it a negative? Well, because it's endothermic, it's a positive. If it's in the reactant side, this is a positive change in energy. If it was in the product side, it would be a negative change in energy because it would be exothermic, and this is our answer for that. All right, so let's go ahead and do this particular problem. This problem is just like the other problem, except this one is giving us kilojoules of energy, and we're asked to calculate how many grams of propane. All right, so first off, let's go ahead and answer number 7. Number 7 is asking if it's endothermic or exothermic. Because the delta H, it's telling us is negative 2220. Because it's a negative, that means it's exothermic. Now what we want to do is we want to write a balanced chemical equation for this. Now the delta H of this reaction, it says, is negative 2,220 kilojoules per mole. Now what I want to do is I'm going to put this within the equation itself to make a thermochemical equation. And so my question is, should I put this on the reactant side or the product side? So I want you to think about that. Should I put it on the reactant side or the product side? And I'll give you a hint. The fact that this is negative tells you which one is which. Well, because it is negative, that means it's being released. That means it goes on the product side. And what I'm going to do is I'm going to incorrectly write it over there. Okay. So I incorrectly wrote it over here. And the reason why it's not correct is because even though this is a negative, when you write it in the product side, you still do it as a positive. So it's not that it's a positive, it's that this negative means that this here is losing energy. That energy is just part of the product. So it's just saying that that is a product of this reaction, is a release of energy. So just keep that in mind, that when we write it within the chemical, the thermochemical equation, we still say plus 2,220. When we write it outside, we say that the change in enthalpy of this here is a negative change in enthalpy. And that just tells us that it's exothermic. So let's go ahead and take a look here. What we're looking for is grams of propane. All right. So it says, you know, how many grams of propane is required to release this many kilojoules of heat. And so again, just like this problem here, if we had moles of one substance, we can convert it to kilojoules using the thermochemical equation. Well, in this situation, if we have kilojoules, we can go from kilojoules to moles of that substance. We can go to moles of a substance. And then once we know moles of that substance, we can then convert it to grams of that substance. And just a little side note, we learned this little part all the way back in Unit 2. We've been using it this whole year, just kind of a crazy thing to think about. But anyway, so we're starting here. We're going from this to moles to this. Now, something that I want to point out is this is releasing 5,550, so it's a negative 5,550 kilojoules. And we're going to go from kilojoules to moles, and then we're going to go from moles to grams. And again, this is moles of CH3, grams of CH3. And we know that 1 mole of this produces 2,220 kilojoules. And so notice how, because this is a negative and this is a negative here, and the negatives cancel out. And then we know 1 mole of C3H8 is the molar mass in grams, which carbon is 12. 12 times 3 is 36. Hydrogen is 8. 8 plus, I'm sorry, hydrogen is 1, but there's 8 hydrogens. 36 plus 8 is 44. And then we just type this in our calculator, and we end up with 110 grams of C3H8. And that's it. So what this is saying is, if we want to produce this many kilojoules of heat, we would need to burn 110 grams of propane. And so this actually is a very practical thing for practical equation that is used actually quite a bit within HVAC. People who work in HVAC, and they can, try to calculate how much energy output a certain piece of equipment will give off and all that. And they figure out what how big of an area can be heated by a certain furnace or whatever. So, but anyways, so we did go through a lot. Just to go over it real quick, we talked about energy diagrams. Essentially, this represents an exothermic reaction. This represents an endothermic reaction. This first part right here is the breaking of bonds. This second part right here is the forming of bonds. This is a greater release in energy in the forming of bonds. This happens to be a smaller release in energy in the forming of bonds. Notice how for endothermic reactions, which absorb energy, energy is always written in the reactant side. For exothermic, energy is written in the product side. And then we talked about how to actually calculate the delta H of a reaction. All right, so you just look at where it starts, where it finishes. If it drops down, it's negative. If it goes up, it's positive. We did this equation here where we figured out how much energy is absorbed or released given a certain amount of moles. We also talked about how to calculate how many grams there are within a certain amount of or how many grams will be required to produce a certain amount of energy. And then we also talked about the whole bond energy and the breaking of bonds. And so again, this last part here, you won't actually have to calculate this at all. I just showed this to you so that you can understand that when bonds are breaking, energy is absorbed. When bonds are forming, energy is released, and it's the difference in those absorbing energy and releasing energy that makes the delta H. So that's it. I know this was a long guided practice problem video, but we did cover quite a bit, and we're going to cover more of this in class. All right, well, have a great day.